Hello, welcome to my channels. In this video, we are going to walk through this example. You are asked to design a Chebyshev low-pass filter that satisfies the following requirements. The order of the filter is 5. The passband ripple is 0.5 dB. The reference impedance is 50 ohm. And the corner frequency is 3 gigahertz. Okay, so we are ready now. So to start with, we need to know the order of the figure. The order of the filter is 5. This means n equals to 5. The passband ripples 0.5 dB. Then we need this piece of information to generate the filter coefficients. And finally, the reference impedance frequency. This could be addressed later. Okay? So n is equal to 5. And according to my software, or according to the prototype table, G1 is equals to 1.7058, G2 is equals to 1.2296, G3 is equals to 2.5408. G4 is 1.2296 again, and G5 is 1.705, and finally we add one more stage for the final stage. Now, the next thing that we need to do is to construct the schematic based on the filter coefficients here. And we know that the order is 5, then there should be 6 stages. And the filter should be like this. Enough. Okay, enough. So this one is G1, and this one is G2, G3, G4, G5. So this is the schematic. And we are going to assume the reference impedance is 1 ohm first, and later we will scale it up. 1 ohm. Now the next step that we need is to use Riches transformation to convert all the capacitor into open circuit stop, and all the inductor will be replaced with an uh, short circuit stop. So the next step is, so this is so-called short circuit stop with the length uh, equal to lambda G divided by A. G2, G4, and here we will use open circuit stop to handle this. This one will become 1 over G1, and this one is 1 over G3, and this one is 1 over G5. And obviously, we need to terminate the filter with the in output port, but we don't do it in VDA. There's a reason. The filter itself needs some adjustment before you can move on to the next step. First, we need to add the impedance sections here. The transmission line section, a short transmission line section. The characteristic impedance of this transmission line section is 1. And the length here is obviously 90G divided by 8. So before we add the low impedance here, we do that. And adding the transmission line sections here is not going to affect the filter performance. And similarly, we are going to do the same here. And the characteristic impedance is 1. And then so this is the result after Riches transformation. Now the next stage is to use corona identities to replace all the short circuit stops with open circuit stop. The idea is to apply two of the important corona identities. But before doing this, we need to be very careful. We have more than 3 stages, so the methodology is slightly different. What we want to do now is we convert this using corona identity number 1. So if you use it carefully, you will get so this is G5, right? So what we will get is we will get this one will become transmission line. The characteristic impedance here is 1 over G5, and then 1 plus 1 over G5. Because the impedance here is 1, so that's why we have this formula. And this one here will become an inductor, a short circuit stop. The characteristic impedance for this one is going to be 1 1 plus 1.G5. So I hope this is clear enough. Make it more clear. And we don't add the low resistance here yet. It's counterproductive. So we delete it. So if we can do that, we can equally do the same for the first stage. So we can do the same for the first stage. So this and this are just mirroring with each other. So this one will become like this. So another transmission line section, the characteristic impedance is going to be 1, 1. And then the transmission line here will become a short circuit stop with the characteristic impedance equals to 1 over So I hope this is clear. So you still have the other stuff, right? But we just copy. Yeah, the middle. We don't do it. We don't do anything for these two. So G2 and G4. We don't need to do anything. And the middle one, 1 over G3. Now, it appears that it doesn't have much, but miracle comes if you add one more transmission line sections here with the characteristic impedance being equals to 1. So 1 and 1. And then we add the input impedance, the loading impedance, yeah, we add it. So now we have a circuit like this. It looks very complicated, but if you take a look at each of the stages here, this one here has the transmission line section connected with a short circuit stop in series. And this one is the same. And this one is the same, just mirror. And this one is the same. So now all we need to do is to apply Kuroda identity, number 2, to convert all this stuff. So let me do it carefully. And before doing this, what I need to do is work out the numerical values here. And if you do it carefully, 1 divided by 1 plus 1 over G1 is equals to 0.63. So if this one is 0.63, then this one is also 0.63. And the impedance here is 1. And this is what we need, 1. And G2 will remain G2. G2 is 1.2296. And this one here is also 1.2296. Yeah, you can check the product table, or you just use the symmetry to guess it. And this one here, 1 divided by G1 bracket 1 plus 1 over G1. And according to my calculation here, it is 0.3696. And similarly, this one is 0.3696. So now it's pretty clear now. We can move on to the next stage. The next stage is to convert this one into a transmission line section together with an open circuit stop. The impedance here can be calculated. According to my calculation, the way how we calculate this is yeah, let's see. Let's check it. 1 times 1 plus 1 over 0.3. And let's calculate this. 1 plus 1. So the answer is right. So what we need to do is to use the same technique. Here, the characteristic impedance here is 1 plus 1 divided by 60. So this will become 258. And similarly, we use a similar formula, but the this one will be 0.63 in times. So you do it carefully, you will get 1.63. And if you do it carefully, and we are now dealing with the second stage, this one will become an open circuit stop, and you will get 0.3696 times 1 plus 0.3696 divided by 12296. So we have to do it very carefully. Let me see, 1 plus 0.3696 3696. So according to my calculations here is this one 0.48. And similarly, this one will be replaced with and the characteristic impedance here is can be calculated with 1.2296 times 1 plus 0.3696. So the answer I have got here is 1.5992. Yeah, I am going to use the red pen to highlight it. 1.5992. So basically, this is done. The middle one here will be unchanged. 1 over G3 is 0.3936. Okay, so the rest will be just a copy. So this one will be matched to here 1.5992, and this one will be the same, and this one will be copy across 1.63, and this one will be. So basically the most important part of the filter is done. So the next stage is to scale up all the impedances to the value based on the reference value, and I'm going to do it. So this one here will be 2.58 times 50. 129, 129. This one here, 1.63. 81.5. This one here will be 24. This one here will be 77.95. Sorry, I got to type the number. It will be 79.95. And this one here will be 19.68. Okay, so the rest is just a mirror copy of the right way of the value on the left. $24, 81.5, and this one will be 129. Okay, so this is our filter. The length of this transmission line section will be equal to lambda g divided by 8. And lambda, yeah, let's assume we are using air as a medium. So and we divide this by 3 gigahertz. (0.1 divided by 8). So it's 12.5 millimeter. Okay. So if you have any questions regarding the design of this filter, please let me know. You can either come to see me in my office or leave your questions to the comment sections. Thank you.